before we keep going to obtain the temperature distribution, I would like to emphasize the difference between external flows and internal flows, because they all come to our final. The external flow we learned last week, and the internal flows we will learn today and this entire week. Internal flow. To determine whether it is laminar or turbulence, what should we do for external flow? Calculate the Reynolds number. For flat plate, you use the plate thickness, the length as the characteristic length. For cylinder or sphere, you use diameter as a characteristic length. And we know that for flat plate, the critical Reynolds number is like 5 times 10⁵. For internal flows, as we learned today, we also have Reynolds number, but defined based on mean velocity of the fluid inside, diameter of the tube, and we will discuss for non-circular tubes what we do here. We'll have modifications over the kinematic viscosity of the fluid. For internal flows, critical Reynolds number is much smaller, and the onset of the turbulence is just more or less like 2,300. And we learn a new concept today, entry length. Does this concept apply to external flow? No, because the boundary layer can expand as much as it wants, not applicable. And for internal flows, we have hydrodynamic considerations. We need to calculate fully developed hydrodynamic entry length and compared with the length of the tube to see whether the velocity profile has already fully developed into a parabolic profile. We also learned fully developed thermal entry length to see whether thermal profile is fully developed. I have a question for you guys. About velocity profile, it keeps unchanged once it achieves this parabolic shape. How about thermal profile, temperature profile? Consider the case if we have a hotter tube and the fluid inside the tube is colder, which means it will get heated by the fluid. Once it reaches the fully developed region, where the temperature profile stays unchanged along the length of the tube, just as what we have for velocity profile. Or no, just by intuition. Yes, the temperature profile will keep unchanged. No. The tube is hot, right? And the fluid is get heated. If the tube is maintained at that hotter temperature, at the very, very end, everything should be achieved at the same temperature, right? Temperature profile changes even after reach the fully developed region. What happens there? Why should that not look like the same as our velocity profile? Actually, if you guys feel, we will learn that later next week by establish our energy rate balance. But if you feel interested, you can go to book 8.3.2 to see the relative shape of the temperature distribution keep unchanged. Note the temperature distribution itself. The book by do normalization and then solve the Navier-Stokes equation, heat diffusion equation, then you can get a normalized temperature profile unchanged. But my conclusion is that even you Once it reaches the fully developed region, maximum temperature is twice as that of the maximum velocity is twice as the mean velocity. But for temperature, no. Not necessary. It's not parabolic decay anymore. As we just discussed, the temperature distribution is much more complex as the simple parabolic velocity profile. This is book point and heat from the tube. Let's go back to the case. We have a hotter fluid, the hotter tube, which heats up the fluid inside. And the surface temperature of the tube is as Ts. And let's say I would like to look at what happens for the fluid inside the tube. So let's say for the heating case, Tm here is the mean temperature, not the maximum temperature. Mean temperature is the mean value of temperature across over the cross-sectional area. If the surface of the tube larger than the mean temperature of the fluid, which means it is a heating case, the fluid inside is going to be heated up by the tube. So it will obtain heat from the tube surface through what kind of heat transfer mechanisms on the second class of second week? Convection, yes. And we know for convective heat flux, for a hotter surface, which is given by the convection heat transfer coefficient times the temperature difference given by the hotter temperature minus, for long ago, the second week we know minus the T infinity, that of the outer fluid. But how about here? We don't have a T infinity here, right? What should we put there to calculate the temperature difference?
The mean temperature.
Yes, mean temperature. That's the way we define convective heat flux in internal flows. Temperature difference given by surface temperature minus that the mean temperature of the internal flows. This is given by the equation 827 inside our textbook. And we would know that how the temperature distributes also depends on the surface conditions, whether the surface material has a constant temperature or material has a constant heat flux, like so much like we learned the boundary conditions. We will go through that later, next class. But by now, if I say, how can we deal with this H? Qualitatively, we have H here. How would it vary along the length of our tube? Yes, qualitatively, you guys are right. It should decrease first, because don't write it down, but in external flows, we learn H is a ratio, bless you, with the conductivity over that of the thermal boundary layer, right? Conductivity almost the same. So the thermal boundary layer start from zero here, which means we have a very large value convection transfer coefficient at the inlet of the tube, and it keep expand once it reaches the thermal entry length, right? As the K almost the same, thermal boundary layer keeps increase. Your local convection heat transfer coefficient decrease, but not approaching zero. For external flow, it approaches zero because YCT, our thermal boundary layer, can expand as much as it wants. But for this case, it stops once it merges at the center line and maintain constant. We did the length of the tube where it remain constant is the fully developed thermal entry length. And now our convection heat transfer coefficient remain constant. And along the rest part of the tube. That's the main difference. For internal flow, it keeps approaching to zero, but for internal flow, no. The thermal boundary layer merge at the entry length, then keep constant.